And with that, I will go ahead and move along to our next talk from Gabriele Bunkheila from MathWorks. So today, Gabriele is going to talk about how to build a neural audio plugin using MATLAB. So over to you, Gabriele.
Alrighty, so I hope my screen is visible. Right now I don't have the live stream in view.
Yep.
So great. So thanks, Josh, and well done to the previous presenter. Really enjoyed the presentation. And it's nice to see that you'll see some of those themes recurring here as well. All right, so for me, I've got about an hour of material. I'm sitting in my Madrid home office, so not as late as in Japan. It's getting to about 8 p.m. here. So this presentation will be about MATLAB, right? And often when you got a presentation about MATLAB, it's about learning a bit of MATLAB. Well, that's not really going to happen in this 1 hour. It's not enough. 1 hour is not enough to learn a new programming language. And so this hour needed to be a bit more focused. So this hour will be mostly about MATLAB and audio plugins and MATLAB and deep learning. And in doing that, obviously, there'll be a few more ingredients that will be relevant to the NAP competition. But I have a few more resources on how to get started with MATLAB more generally, but not in this 1 hour really. So let's keep in mind, these will be our two main topics, roughly half each, obviously interleaved and related. Quickly about me. I've been with MathWorks for about 15 years, and these days I work in product management. I work in a toolbox of MATLAB. It's called Audio Toolbox, but I also have an oversight of other toolboxes in general for signal processing. I have been using myself MATLAB for going almost to 25 years. It means that I started a long time ago. Those days, neural networks was a course in physics. All you studied about neural networks, very theoretical. And so that means also my core background is not in deep learning, although as a DSP person, as the bottom item here, obviously I got a bit up to speed with that. Good to know if you have questions. That my main background is in audio and DSP. So I first studied physics and I have a PhD in comms engineering. All right, so since I was saying that, obviously in 1 hour we won't cover anything. First of all, where do you go if any of the information that you see during this hour sounds interesting? But we have a page on in support of the NAP competition on mathworks.com. The little thing below is the actual link. Oh, by the way, a few minutes ago, my fast clicking finger, I got it wrong. I posted on the chat while Newton guys were finishing the presentation. Not very polite. It wasn't on purpose, but you got a link to the PDF version of the slides there where all these hyperlinks should be clickable. So go and grab it from a few chat messages above. What do you find in this page? Two things to remember. There's one section full of links with some technical resources. There's some tutorial demos, some videos that go a bit more in detail, especially about plugins and deep learning. Now there's a button to download a MATLAB license for free if you're a student. So that caveat. You need to show that you are involved in some kind of education and we'll give you access to a good stock fit for purpose for this competition. If you really want to start to learn about the basics of MATLAB these days, there's a lot of kind of short few-hour courses for getting started on our website. Left-hand side, we got the basics, but there are some short getting started courses on deep learning and signal processing that might be worth a look if you are not very experienced and you wanted to get started. If you get stuck, I have to say that, yeah, MATLAB is known to have one of the best documentations for software tools. And for me, it's quite a disadvantage because these days I get nervous quite quickly when I use another software tool. But if you get started with MATLAB and use to something else, that makes it quite easy to solve your problems in the doc. There's also the community to ask questions. It's called MATLAB Answers. And if you've got a more specific question, feel free to reach out through LinkedIn or whatever other means. So getting back to our topics, The first focus will be on what MATLAB has to do these days with audio plugins specifically, because since when we launched Audio Toolbox about 6 years ago, we introduced a few tools specific for audio plugins. And so we'll be taking a look at how to write MATLAB code to do audio plugins. That will be MATLAB code first, how to translate that MATLAB code into native binary VST and AU plugin using MATLAB. And then we're also taking a look at how to then incorporate these networks into, first of all, the MATLAB plugins in a way that will be translatable, convertible into a piece of native software. So to start, I just want to play a kind of a couple animations from a demo I put together a few years ago that has some deep learning in it. And I think it gives you a bit of the idea of where kind of the middle point of where MATLAB is used in engineering. It's this possibly, a lot of companies that do a DSP for music, they use MATLAB, but across the board, there's many more people using MATLAB. And so when we put together these automations, let's call them, to turn MATLAB code into a native plugins, the idea is not to make plugins for creative operations on content. In fact, we don't do any creation of instrument plugin, which is a bit of a bummer, but hey, you can't do everything. And so we need to be selective. So our focus for the plugins was to make audio engineers, acoustics engineers, speech engineers a little bit more productive. So to give them a way to prototype whatever DSP or machine learning algorithm, not specifically to do production, to work in music or to work in DAW, use the DAW basically as a way to see how a kind of a dry MATLAB algorithm would sound in real time. So this example is about wake-up word detection, right? So the main application, I'm sure you know what I'm talking about. Hey Siri. Is this, right? This is my shabby old office. And then if you look at this from a MATLAB perspective, some of the general idea is that when we write the code to prototype something like a wake-up word detector, we have all the logic in place to buffer an input signal as it streams through the algorithm. In general, in this case, to extract features or do some kind of transformation very often, to feed those to a network, and then to do the inference. These three things, generally, it will look like pseudocode is actually MATLAB code. Will look like these kind of the core of the maths. There's some MFCC Fisher structure in this case, normalized and then passed into the classifying method of a deep network. And then there's a bit of post-processing to do some debouncing of the detection and to generate a sound. All these things go into some wrapper code that we'll take a look at in a bit of details in a few minutes. And then what you did with this wrapper code, which is MATLAB code, is that you call a command called generate audio plugin. This is the API. There's also some apps where to do this. And as you do that, that gets, first of all, translated into C++, wrapped into a Juice project under the hood without you knowing it, and then built with the format that you select. And as a result, you've got, in this case, your VST, this is Reaper. And so in this case, it was.
Okay, I'm testing a prototype of a wake-up word detector, trained to wake up when it hears the word yes.
All right, so that was played
to wake up whenever
in the plugin.
Says yes, but obviously not when they speak any other random word that's not yes.
I'm showing this a bit to make fun of myself, right? Obviously, you're not going to make music for this, right? And it's true that you won't find in MATLAB any super duper example to make great music. You'll have to inject quite a bit of creativity and pre-existing idea, I guess, to do something useful in the next 2 weeks. We won't get there. What we do is turn some DSP and deep learning code written in MATLAB into something that can be auditioned in real time. All right, so this slide is, in a very compact way, of a way to give you, from a very high level perspective, the basics of putting together a plugin using MATLAB code. What is this about? This is a high-pass filter. There's no deep learning in here. It's like close to the simplest thing that you could do without being too trivial. So what is this? You can see, I hope you don't have this ugly Zoom toolbar at the top. You can see that the first line it doesn't begin, if you're familiar with MATLAB, with a simple function header. It's a class definition. We use classes to enable you to wrap up plug-in code and inject the right metadata in here, because it gives a way to put the right stuff in the right places. First of all, this class inherits from an abstract class called audio plugin, and it's got some basics rules in how to expose things. Parameters of the plugin is first declared as public properties, so they're visible from the user. You always provide a method that's called process. That method, this is just the this pointer, as you would call it in C++. So it's just got an input and an output. The number of columns in the input will say how many channels you're passing in. And then the other thing about classes they give you property of the classes as routine and data property. What do you do with properties? Well, you do useful things for real-time audio. For example, you store states for any arguments.states, like in this case a filter, hence choosing at least a filter. In the case when we process, we pass the current state of the filter inside the filter function, and we export the filter the updated states and we save them again. So fairly trivial. And I also know typical useful things is that you store results of expensive computations. If you want to expose the cutoff frequency of a filter, well, you don't use the cutoff frequency itself to do the actual convolution. You first need to turn that cutoff into some filter coefficients. You only want to do it when it's useful, not every time. And so then you use the property to store things. Anyway, this is fully documented, but this is the gist to get. You need to write a class in MATLAB to auto plugins. Okay. When you then use something like this, you create an instance of that class. You call that an object. Okay, and that object will expose the what you created as parameters. So you then change it using, for example, the dot notation by referencing the property, and you use the process method to pass an array and take out the output. You can use either the dot notation or the function notation, where the object is the first input, the object instance, right? So when you do things this way, it means that you enable MATLAB to parse this object and to understand how to automate a few things. So the parameter, in this case, you declared it as a parameter, but you need to pass a few more information in order for MATLAB to automate drawing of an interface. What does an interface need as a bare minimum? Well, it needs kind of a name that could take it from here, but it needs to know between what range you need to change the parameters. You want a minimum, a maximum, and also possibly a variation low, because for frequency, you don't want to go linear. So there's something else that you tend to add to these objects, some metadata that's called plugin interface, where you basically give that information. Optionally, you want to give the units, you want to give a variation low, in this case, logarithmic, from a minimum of 20 to a maximum of 2000 in this case. And that's pretty much it. Okay, once you provide this, then it means that you can take the code and also automate the rendering of a user interface. And you can do that in a few tools inside MATLAB. We'll take a look, for example, this audio test bench that allows you to connect algorithms or plugins to inputs and outputs, for example, file content or input from your sound card. But also, utilities to build interfaces to this object you can use while using the object in a script, for example, and still tune the value of the parameters through an interface. So these are used inside MATLAB, but also outside MATLAB. When you take this plugin, which is called ipass.m, and you call this generator plugin, you will generate the binary, and generate the binary with an interface. These days, that interface can also be slightly customized. The things that we're trying to help people are easy things. So there's no visualization as yet, but there's a few flavors in which you could have control over parameters, depending on whether they're continuous. They could be knobs or sliders, but they could be also switch and drop down menus. So there's a little bit of customization by using film strips, which are long images that are collections of all the 256 aspects that a control might have. You could customize your controls however you want. Now, this is the small print that you find at the bottom of a box when you buy something. What are the things you can do and cannot do with these automations? Let's go. So, as I mentioned previously, this is centered around effects. There's no virtual instruments. You can put together, you create sources, but all the media automations with that's got to do with nodes, there's no automation for that at this stage. We are, we are keeping, improving the type of standards that we support, the types of plugin. You see in these slides, wherever you see R, a year, and an A or a B, that's the tag of our release. We do 2 releases a year. The A in the spring, it's about to come out in March, hence the coming soon. We don't really like to say when things are coming up, not to commit to anything that we're not super sure. But so although 23A is coming up soon, you won't see any mention to 23A in these slides. But there you go. So we keep incrementally improving these capabilities, although the first release was delivered in 2016. So these could be VST, AU, they can be standalone. And since it doesn't say since when, but since a few years ago, we also give the possibility to generate source C++ projects. So instead of relying on all our automations, you can use your automation up to the point of generating a project. And if you are a fancier, for example, interface or something else, you can take over the generated code and moving forward with the project. All right, where to go for examples and inspiration? I want to show these 2 links. So there's the place on the left is a place of the MATLAB documentation with plenty of examples that are open code, just that you can dive in and explore. The right-hand side is the historical file sharing repositories for MATLAB community. It's been around for ages. And since launching the MATLAB plugin competition with the Audio Engineering Society, we're putting here a tag. And so by using this AES-COM tag, you get all the submissions to the past competitions. And 2 things to mention, to highlight, and kudos to Christian Steinmetz, who is not joining us today, but is helping the audio plugin competition. He, for me, was one of the best contributors to this. He came up with a very smart use of deep networks that don't just produce, consume and filter audio, but work on automating the production parameters for plugins. And I think those are 2 great examples of use of deep networks. But what I wanted to show you here was this page, because this will help us go a bit into MATLAB and take a look at this. So you can see this page. It's useful because it gives you an example of how to customize the interface using the API that we use, and with very simple effects that many people know. And so once you know the effect, you look at the code and it makes sense and it helps you learn. At the bottom of this, there's only 1 example on deep learning, which it's a denoiser. Don't get too excited. This is not like the denoiser that Adobe released a few months ago, or the ones that's used, I'm sure, by Zoom and Teams. This is a very crude denoiser, just a basic denoiser to get you used to the general idea. It's linked to another example that we ship. I'll just quickly show this to you. It's called Denoise Speech using deep learning networks. And this example gives you a couple of choices between kind of a convolutional network and a fully connected, and the plugin uses the fully connected. It's based out of a very crude idea that people were experimenting with a few years ago, up to 5 years ago. It's just short time Fourier transform fed into the network that sees the latest 8 frames of the short time Fourier transforms. It's given the latest, the current as target to minimize the distance between the 2, and it basically spits out a magnitude estimate, and phases reconstructed from the input. Really a crude, but the crudeness is good because you can concentrate on the flow in this case. So I'm not claiming this is actually any good, and we'll see how it sounds. Going back here, you can see that this bit of page has a click to inspect the code to actually generate the plugin right from here. And also, in this case, it gives you instruction of how to download the actual networks. Most deep networks that ship with MATLAB, and I'll give an overview in a few minutes, they don't ship with the installer. not to oblige people to install, tens and hundreds of gigabytes for folks that don't use them. So you first need to go and download those from mathworks.com, and it says you how to deserialize and then save it locally so that plugin seeds can use it. But if I go then in MATLAB, that's how the plugin looks. I just want to walk you quickly through the code to recognize a few patterns together. The header, there's the class name, and then also this minor audio plugin. That means inherit from abstract class audio plugin. That's how plugins are named in MATLAB. That's the plugin type in MATLAB. As we scroll down, the first thing we meet are a few public properties. So the things that you see from the outside world. Okay, and there's some of that horrible information and code to configure the ranges of this is copy paste code. It creates a simple interface where you define whether you want a kind of a knob, where you want it in the grid that you instantiate, and what kind of the variation laws you want to ask for those. This is something that I don't want to discuss now, but this is something that says how to optimize the DSP and the deep learning layers of the network that you use using the local CPU, so using optimization libraries. And then we go into a bit more interesting things. The heart of everything is the process method. I was saying this is the this pointer. This is the input audio, and this is the output audio. So what happens in between? This is where everything takes place. Every time a new frame is passed by the DAW or by MATLAB, depending who runs this, then this method is called, and something happens to that little buffer. The buffer is simply what the DAW gives you. It's not the buffer that the network needs to see, as the Newton guys. I love your slides, guys. I think they were really nicely made, and they explain what the concept. So what we're seeing there is similar to the stuff that you automate without the user needing to worry. Here, the user has to worry a bit. The point of no worries comes from reusing examples like this, but the code is here. So what happens here is that we get the audio being, for example, converted to 8 kilohertz, because that's the rate that the network in this case was trained to. And also taking, so that's the decimation. We write also to a longer buffer to make sure that the network gets called only when we got enough samples for it to be used. And then you see here that we've got a bit of a a short time Fourier transform right into the buffer. And then in this case, in this line 2024, we're calling the denoise model. And then once you call the noise model, we reinvert into the time domain. And we write to the buffer, we read back from the buffer, and convert from 8 kilohertz to whatever sample rate is passed by the DAW, and we're ready to create the audio. What's in the denoise function? Well, you see that's the heart. This is the brain. And this is where deep learning happens. This is the deep learning prediction. So this network was pre-trained, serialized into a MATLAB format, and in this case, it is a MATLAB network, and it's read from a file in an agile serialized format into this object, which is persistent. So this is just an example of pattern to have things persist over calls, and then you call the predict method on that to produce the output of the network. So that's it. From a user perspective, how do you use that? So let's call, for example, an instance of this. An audio plugin example is the package where we show all the examples in the doc. And so if we let this display what we can see, the user can see the parameters that were specified basically in that interface. And if you do dn dot threshold, you can change to this. That's obviously changed. That's how you change it programmatically. If you have, for example, this is a bit of noisy audio. We can call this that I created with a simple script previously. Okay, so, audio NFS. We load this into the workspace. So this is a bit of noisy audio. If we listen to this,
The discrete Fourier transform of a real valued signal is conjugate symmetric.
all right, so this is just a dummy voice that's been around in MATLAB for ages, and then washing machine from, I think, some Mozilla data set, just to experiment with noises. And this network was only trained on removing noise machine noise, and it doesn't do it all that brilliantly, because it's an example. But some of the things that the DAW would do is that it would, for example, set from the outside the sample rate, and so we make sure that this we set the sample rate to the plugin, so the plugin is aware, and when it needs to do the decimation and the interpolation, it knows what are the input and output signals. And then we can say that our output is the n dot process of our input. And so our input was a single channel, that's the number of columns of that many samples. And so the output will be just as many samples of a single column. That's what we can expect. And that's it. Will it be very clean? We can try.
The discrete Fourier transform of a real valued signal is conjugate symmetric.
How better than the other one?
The discrete Fourier transform of a real valued signal is conjugate symmetric.
Not quite right. No miracles. Right. So old model, basic principle, no brilliant latent space. It's just a mask on the short time Fourier transform. But the idea, I think, is what counts. Other things that I wanted to show you, and I'll quickly bring up something for me on the other screen to make sure that I don't forget about two things, is this audio test bench. So if you go to MATLAB's got a number of built-in apps, and under here signal processing, you'll find this audio test bench. You click on it, will bring this up. This is, I showed this in one of the slides before. So say that we got this as denoiser, or we can also put the N here. This will bring in our object, and you see that it will render the interface based on the metadata that we put in the plugin. So we don't have to design the interface using MATLAB App Designer or Guide or whatever. This will do it for us based on that metadata. And so this is the place where I can directly hook this up to a file, for example, or an audio source, or kind of the device reader from any sound card. I can put this in the loop or bypass, in this case, right to the output. So you should hear it. And as I then run this, jumping around, isn't it? It's just about, in this case, if you run it without compilation, to do the right job without kind of a live YouTube live stream or a Zoom connectivity. But the other things that I could do here is also to load the binary version of the plugin. Okay, so for example, if I did like that and load the compile plugin, and so this could be a plugin that I generated with MATLAB or any other plugin, because MATLAB can also host binary, VST, or other plugins, then it will take focus away from me in this case and then give it back. So that will you can see that when we import another plugin, we don't honor the plugin UI. We just paint a basic UI based on the definitions of the parameters, and this might well be
The discrete Fourier transform of a real valued
bit faster.
signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform.
Really not the end of the world, but at least you can hear the difference. You can at least it's confirming and it's doing something. Okay, and all right, so I'll go over things like MIDI connectivity later on using slides. What I want to point out here is that this is a nice place to show you the idea of doing real-time audio in MATLAB in general. If you click that generate MATLAB code from the app, it shows you the basic principles of running live MATLAB algorithm on live audio. And it's not that difficult. The basic idea is a loop. It can be a while or a full loop. I remember back in 2000 when I started using MATLAB that I had this idea of writing a simple loop and doing audio processing real time. Obviously, it didn't work those times. But the idea here is that you're using objects to read from files or a sound interface. So all the initialization and memory allocation to deal with the communication with the driver is done outside of the loop. And then what we're doing inside the loop is just shifting the pointer to the audio buffer. And so in MATLAB, it's quite easy these days to do real-time audio, just writing code. You don't need to go to the app, but the app can make life easier for some people. In this case, this system under test was the hosted plugin, which was the VST2 in this case plugin, that was rendered as a MATLAB object. So if we run this in isolation like this, you can see that SUT will be called a VST plugin denoiser with the variables that it exposes. And so this gives you a way to test plugins in a non-interactive way, in a programmatic way. If you need, for example, to verify that the plugin outputs the right output for a given test signal, you can use MATLAB for that. Why do I say you these things? Because I don't believe that you must use always one tool, just MATLAB to do all the job. MATLAB may have a few things that might help you in the process while using other tools too. All right, let me I haven't showed something around the network that's in here. So let me quickly say about things. You remember that the network was saved into this file, or that was what the example was recommending. So if I take this and take a look at it at the command line and see what this is, it tells me this is a serious network with a few layers. So if I type the name again and ask for the layers, it will show me what the layers are. And so it's got an image input. Well, it was working on that short-time Fourier transform, so that's the way we call it. It's a 2D input layer, and then it had a number of fully connected layer following, right? And so if you then go here and you feel that you want to investigate, for example, what's in layer number 8, that you got the details for every layer. So you got the typical MATLAB ability to interact with this. Another thing that you can do, well, another approach, let's say, to look at networks and to deal with networks is through apps. This app called Deep Network Designer. In this case, we're looking at this and at this network that you got here saved in our workspace. Denoise fully collected network, that's the one, and we import it. It will give us kind of a visual representation of the network, and this app gives us a way to, this is a visual representation of the network. From here, I can select, move around, delete, drag other layers from here, and for every layer, then possibly customize all the parameters in here. There are some, let's call it DDSP layers in here, like the STFC to use. Go look at the example. Obviously, I can't cover everything. I'm fearful that I'm going into too much detail here. Let me jump out of MATLAB and go back to the slides to make sure that you have all the key bits of information here. We went through this example, and we talked about loading plugins in MATLAB, or hosting, as we might say. All right. Now, something that I hadn't showed through the app is how to do another kind of automation. When we've got the plugins with their parameters, we can change them numerically through the API programmatically. We can change them through those apps that I showed by turning with the mouse pointer, or we can link those parameters to MIDI controls. So if I run this command, configure MIDI on the denoiser, you remember maybe, hopefully, that it had these 5 parameters. And so what do you do is that it gives you this this UI. You click on one parameter, you go to your the surface, controlled surface, you touch your control, MATLAB senses what you touched, and immediately locks the plugin parameter to the controlled. And so even if you're using the plugin in code, by moving the media controls online, offline, while you execute the code, while you don't execute the code, the audio plugin in MATLAB will reflect the position of the control. All right. Useful for a few workflows. All right. I can't believe you. I'm already halfway. Well, I better be. So that's what I was planning to cover just on audio plugins, but I've started to tell you a bit about deep networks, haven't I? Now is the time to go a bit deeper into discussing deep networks in MATLAB and see a few things about how the whole thing works. And the things that I really would like to cover is the various approaches to how to get hold of a network or design it. The possibility that you have in terms of using MATLAB with PyTorch and TensorFlow, where, as we know, most of models live and are developed. And how do you go then to implementations? Why do I care about this? Not because I want you to take the network and deploy to chips, even though this is what MATLAB users do. But as I said, if we want to plug in, the trick is to take the MATLAB code and convert it into C++ before it gets wrapped with juice rubber. So we need to make sure that when we use a deep network in a MATLAB plugin, that network, as we say, supports the ability to be converted into C++. Ideally, everything does. In practice, not quite everything does. So it's just important to know the fine print. All right. So in general, when we talk about deep networks, probably at this point here, we don't need to say there's a network in the middle, and then there's an input and an output, but those input and output can be different things, right? If in the case that we got a signals and we got a choice, it can be a classifier. Why not developing a plugin that's a classifier? That's also a possibility as a way to prototype an algorithm. It could be a signal processing engine to process the input signals. It can be something that derives some parameters, like some of the work that Kristen had done in that example, for example, by analyzing some signal, understanding which, for example, effect parameters you want to apply for automated mixing, stuff like that, for example. Or in other applications, it's just about extracting deep features that describe the signal. Whatever. All of these things can be done, obviously. And in MATLAB, I would highlight three possible strategies to build a model. Either you can define it from scratch using the app that we've seen and using the equivalent API that we took a glimpse of. MATLAB ships with pre-trained models already in MATLAB that you can. So the ones that we saw together, yes, it was pre-trained. It was pre-elementary and basic, but we ship some state-of-the-art models that could be reused. And those are useful because by doing transfer learning, suddenly you don't have to, if your application is reasonably matched, then you don't have to do the full training. You only have to train a few layers. And the other idea is to import it from another environment. So from TensorFlow and PyTorch, either directly or through ONNX, for example. Those things are various things that are supported. So let's go quickly through those options. We thought about these two conceptually different ways of composing the network. If you're kind of a command line person, there's the full API to build just networks as a topological connections of layers, or you can go drag and drop in the app or mix and match. All right. There's also the ability there's another API in MATLAB to write deep networks by going more into let's say the mass of the layer, by defining the layer by the way of how they works, using some API that makes them auto-differentiable. That's all documented, and I don't want to go too much in detail there, but feel free to go there if you want to learn more about those. And then, as I was saying, these days, MATLAB comes with a number of pre-trained networks. We've got for a couple of years this new GitHub repository that attempts to summarize all these models that are scattered in multiple places, but they're state-of-the-art models. And there's quite a few for audio, speech, and acoustics. So I want to give you an example of what it means when we ship pre-trained models in MATLAB, and I'll use one of these state-of-the-art models. It was developed by Google. It's called YumNet, and what it does is sound type classifications. It's trained on over 500 different sound types, and it's able to classify and segment different contexts of recording. And it's one of the models that we ship, and it's easy to understand. Right, so that's basically what it does. You give it a waveform, it processes it and gives you a choice between over 500 categories. And so it actually, the model doesn't consume the raw audio, the waveform, but it's been trained using a specific strategy for feature instruction times frequency transformation. If I don't remember bad, these are MEL spectrogram, whatever. So what do we do when we ship these networks that are state of the art and pre-trained? We do several things. First of all, we give you the network in the same form that you've seen the denoiser earlier on. So the bare network that can be fed, featured, can be trained, and can be inspected. We have in this case the MEL spectrogram in general, but when you need to extract the right MEL spectrogram that was used to train YumNet, you need to know what kind of window length they used, what kind of band spacing they will use. It's hell to know about all those parameters. And more often than not, you don't get it right. So what we try to do is to package the MEL spectrum we have with the right parameter choices. So you got exactly the same parameter choices to train the network. And you've got also the conversion from whatever sample rate of the signal to the sample rate that the network uses. It's not the first time you hear about those things, right? Today, it's a common pattern. Try to make it easier for people to reuse state-of-the-art networks, as the Newton folks outlined. Why do I say that? Because we also have a kind of new objects that do bag of features for audio extraction, but they can be difficult to use. And then we also provide some helper functions to make something useful of the output. Look at this tree of classes of these ontologies. It's a bit of nightmare. So perhaps you don't care if it's a horn of a lorry. You care just if this is a horn. So you want to be able to look at the right level of hierarchy. But to make it short, we provide helper functions at the input of the network and the output, and then we provide an abstraction for casual users. If you really only want to label sounds for train some other system, you only need to segment. You can use a high-level function called classify sound. You pass it a waveform and the sample rate, and it will give you the regions of interest of some sounds that it found, for example, right? But for this kind of exercise, to build plugin, really, you want to look at this level of abstraction, okay? But so this is a list of the few state-of-the-art models that we supply with the full support of all that kind of abstraction. So layer, kind of casual layer to just do the job, network plus, pre-processing and post-processing helpers. So you can see CREP, for example, for musical pitch estimation here. OpenL3 and Vigish, these are for embedding extraction. If you want to do some more, understanding of the feature, and you want to work on advanced feature, these are good choices. We talked about YumNet vector. iVectors are very useful for speech processing, but actually they're not deep learning. These are systems of traditional deep learning models, and these are the applications here. But there's also that, beyond this, there's a full list of other models where, some of them state of the art, like X vectors, for example. ContestNet is used very much for speech separations, and so not for all these. We've got examples. Some of those are on GitHub. We don't provide the full spectrum, but you still may find useful stuff to reuse in all these resources. And for example, see this. I don't have it here, or do I have it here? The network that I showed you earlier, denoising this one. Okay, Mozilla Common Voice Dataset, the basic CNN receive. Oh, I was wrong here. The one that I showed you was fully connected. It's a recipe. It's pretty old, but yeah, there are other like these. There's a dereverberation one, etc. Now, that's about all MATLAB. Having this allows you to stay in MATLAB. I had a video where I showed what it takes, for example, to transfer learn some of these networks. Let's take a look at that. I think we probably have just about a time to take a look. Let me make sure that I moved out of my presentation, and let me unhide this slide and present it. This is what it takes, for example, to take a pre-trained network and transfer learning. So in this case, we're taking YAMNet to identify some noise of an air compressor, to identify the damage of the air compressor from the noise. So we've got the data sets provided by somebody, and we want to retrain YAMNet on that new data set to have YAMNet understand what kind of damage an air compressor have based on this noise. And so this is YAMNet. If looked inside the Deep Network Designer, we strip away the last classification learner. We only care about classifying between 8 different types of condition of the machinery. We connect, we import the data in the right format, which was that that MEL spectrogram. In this case, you see it, monochromatic representation of the MEL spectrograms, and then train the network with the new data. But because all of the network converged, we're really only training the last layers. And so if you look at the time elapsed here, these are only really few minutes on a CPU in this case, on a single CPU. So that's maybe a nice follow-up to the question and the answer on the impact. Sometimes, especially in industry for industrial applications, much of the suggestion is to reuse, to go on the shoulder of a giant and try to use state-of-the-art models on your own data, and you see, in this case, that's what that example does. All right, what about you don't have the model in MATLAB? There's many ways to take from other environments. I won't maintain that this is straightforward completely and that it always works. Going from one environment to the other is often painful, so it may be that you'll have to go over some little issues, because sometimes, for example, the translator cannot translate one layer from one environment to the other, and it will replace it with an empty layer. Well, you need to go in sometimes and recode or replace the empty layer with the actual corresponding representation. That said, there's the way to do it with ONNX. You can go in and out on TensorFlow, and you can go in from PyTorch into MATLAB these days. Links here to these resources, these pages of documentation. You can see there's plenty of different types of functions to import networks from different environments, sometimes in slightly different ways. So go and focus on whatever is relevant if you need to use a network that was developed by a colleague or is available out there developing another environment. More general, MATLAB is not just about TensorFlow and PyTorch or ONNX. MATLAB can also talk to Python. Why would you want to do that? Many different reasons, but and I'll go through a few, but this, for example, you can use MATLAB as a master and call out to Python. In this case, in this loop, using the forward prediction of a network available in Python. This is the way to call a Python object or a package in this case, or I don't remember what this was exactly, but you basically, these were written in Python, and the code here is all MATLAB. Pretty straightforward. And easier with the years. Same thing is roughly valid from Python as a master as well. The thing to be aware is this MATLAB engine is just basically a programmatic API from MATLAB, and you call with the dot notation things that are on the MATLAB path. So this is, in this case, MATLAB function. So why do you want to do that? Well, for example, this is a possible use case. This is where you've got a framework, Python and TensorFlow, where you've got all the network set up in the training loop, but you want to use MATLAB to label and pre-process or augment your data set because DSP may be simpler there. Well, you just link in the tool, you call out to MATLAB from the Python training loop, and that's also possible, right? There's plenty of resources. I put down 2 possible links. This is about training in Python with MATLAB in the loop. It's a GitHub submission. And this is a page on mathworks.com with various resources on using MATLAB and Python together. Just to strengthen the importance of using MATLAB, thinking out of the box, not just about training and deep learning models, but also all that comes with it. If you work in deep learning, many times 80% of your work is on the data. So there's a lot of work to do around deep learning that's not just about the network. It's about, and sometimes reusing a data set for a different purpose, where you want to have the right tools to the right resampling, the right segmentation, the right signal processing, all that you need. And aside from things specific to labeling and segmentation, MATLAB's got a lot of new things for feature extraction, a lot of new things, for example, for randomized, automated augmentation of audio. See, this is a new object called audio data augmenters that allows you to have either serial or parallel pipeline of augmentation effects that you can control randomly to try and improve the accuracy of your model if you don't have too much data available. Right, so I'm getting into rambling and listing of window shopping capabilities to try and list as many pointers that might be useful. And so without even realizing, I'm getting towards the end of the second part of the presentation, which is good because we're close to the end of the time that I had allocated, although I know I started a little late. So the other thing to know is, once you know about all of these things related to deep learning, what do you need to know to make sure that if you use a deep network in MATLAB, it can be used in the plugin. These are the main ideas. So as we saw with the plugin, it's not just about the network, but it's about the network and all of the MATLAB code that relies around it, the signal processing, the buffering. And so that what we do is to generate C++ from the whole lot. And inside it, there's also the network. So as far as the network, in general, MATLAB can be translated to embedded code for different types of devices. It can generate CUDA, it can generate C and C++ to run CPU with or without optimization libraries, and it can generate also HDL, Verilog, or VHDL. What we really care about here is mainly the CPU root. Well, why didn't I include GPU? MATLAB can generate CUDA. For plugins specifically, we haven't made things any easier, so I won't mention about that. Don't think about generating CUDA from MATLAB while using plugins. If you're not doing audio plugins, that's also possible. But if you are doing plugins, it's beyond recommended. The automations work for C and C++, C++ for plugins, right? And the two things to mention are these. You can choose for your network to go either library free, so basically vanilla C++ for the network layers, or you can choose to use a finite set of optimization libraries. Well, you might think, oh, why are you not using that optimization libraries? I wish. We're not using everything. For plugins, we're allowing ARM optimization for Cortex-A to try to go through Juice project generation into Linux plugins and perhaps being able to run on Cortex-A based things like Raspberry Pi. Although it's not a workflow that's massively used, but it's possible. But the main thing for optimization to look at is Intel. Okay, so think about mainly library free or Intel as the two main options. So here they are: vanilla C++, or as it was once called MKL-DNN. I think these days it's called OpenDNL, and that works on Windows and Mac. Obviously, not M1 Mac, but Intel Mac. And this is a bit, if you got good memory, I said while opening up that plugin code, I said I won't talk about this, but this is important for code generation. So if I go back to my to my MATLAB and my denoiser plugin that I was showing, I had here at the top where I had the metadata. I had something else under here, which was called audio plugin configuration, right? And here I was specifying two parameters: deep learning configuration and code replacement library. Forget about code replacement. This is about the replacement of the DSP. So optimizations, SIMD optimization for things like filters, FIR filters, and stuff like that. But the thing to pay attention for deep learning is this. You got two options here, either MKL-DNN or none. If you put none, then the plugin will generate vanilla C++ when building the library. If you select MKL-DNL, then the plugin will link to the Intel libraries. If you do this, you need first to install the libraries, compile them, making sure they're on the path, you configure your OS, etc. Everything's documented, but it won't just happen the first time that you do it. All right, if you, in terms of support, if you're using a network that's fancy, you don't know whether it will generate code, there's this command that you run on your network in MATLAB, and it will tell you if it supports code generation and which of the optimizations it will support or not. Right? In an ideal world, everything will support every output. In practice, that's not the case. All right. And so I hope with that I'm pretty much honoring what I had set out to talk about. I cover mostly the infrastructure for automating the generation and the hosting plugins, and in general, deep learning, as well as how to use deep learning in plugins. And I hope I touched a few other things that can be relevant for the competition. Josh, you haven't interrupted me. I don't know whether it's too late and people have started to fade away. Or...
No, we're still here. We're still here and we're going strong. Thank you very much, Gabriel.
Good stuff.
For that amazing presentation. Doesn't appear that we have any questions in the live chat. I know that may have been quite a bit of information for people to digest, and that's okay, because we have this video online and you can watch it back, you can slow it down and pause and rewind and loop as much as you'd like. So for people that are using MATLAB, I hope that you've enjoyed that presentation. Once again, there are trial licenses that are available on the MathWorks page that I have linked in the chat for you if you would like to use MATLAB to build your neural audio plugin for the competition. And before we sign off, just wanted to say thanks to you, Gabriele, and thanks to the team from Cosmo, Andrew, Christopher, and now Taki. And thank you very much. I really appreciate your efforts, and I think that a lot of people really got a lot from this. So thank you very much.
Thank you very much for hosting us.
Yeah, thanks for having us, Josh.